Good evening all. Now we are going to see a presentation on thermoelectric effects. Under thermoelectric effects, we are going to see about some basic effects such as Seebeck effect, Peltier effect, and Thomson effect. Let us start with Seebeck effect. Seebeck effect was given by the scientist named Thomas Johann Seebeck in the year 1821. In Seebeck effect, we will be considering two dissimilar metals. Here we are taking two metals as copper and iron. These two dissimilar metals are joined together to form a closed circuit, and if we maintain the two junctions at different temperatures, an EMF is developed in the circuit. Here, one of the junction is kept at the high temperature, that is at hot we are keeping it, and another junction is maintained inside the cubes, ice cubes. Hence, we are maintaining the cold temperature at the other end. This causes a current to flow in the circuit, which can be indicated by the deflection in the galvanometer. This phenomenon of producing the current when two junctions are maintained at different temperatures is called Seebeck effect. The arrangement of two different metals to form two junctions is called thermocouple. The EMF developed in this thermocouple is called thermoelectric EMF. This thermo EMF depends upon the temperature difference between the two junctions of the metals. Seebeck effect is reversible. That is, when we are interchanging the hot and cold temperatures in opposite sides, automatically the current deflection which is shown in the galvanometer will also be in opposite direction. From this, we are able to say the Seebeck effect is reversible. Seebeck, after studying the thermoelectric properties of different pairs of metals, he arranged them in a series called thermoelectric series. The series starts with bismuth, nickel, palladium, platinum, copper, manganese, mercury, lead, tin, gold, silver, zinc, cadmium, iron, and antimony. The direction of current at the hot junction is from the metal occurring earlier in the series to the one occurring later in the series. So we are able to choose any pair to be acting as a thermocouple. If we are choosing the two metals and if the gap between the metals in the given series is small, then the EMF developed between these two metals is found to be less. If we are choosing a thermocouple having the metals lying in the series with large gap, it is able to develop more thermo EMF. The position of the metal in the series will depend upon the temperature. The thermo EMF of any couple has the temperature dependence given by the relation V is equal to alpha theta plus half beta theta square, where this theta is the temperature difference between the junctions and alpha and beta are the constants which depends on the nature of the materials. The next effect which we are going to see is Peltier effect, which was given by the scientist Peltier, who is a French scientist in the year 1834. In Peltier effect, we are considering a copper iron thermocouple or any thermocouple we are considering. And when electric current is passed through the circuit consisting of two dissimilar metals, heat is evolved at one junction and heat is absorbed at the other junction. This effect is called Peltier effect. This Peltier effect is the converse of Seebeck effect. How? In Seebeck effect, we are giving the temperature, we are giving the two different temperatures of two junctions. One is hot and one is cold. Then automatically current is produced. But in Peltier effect, we are passing the electric current and due to that, two different temperature junctions are produced. One is hot and another one is cold. Hence, we are able to say Peltier effect is the converse of Seebeck effect. When the direction of the current is reversed, when the direction of the current is reversed, automatically the junctions also gets interchanged. The junction 1 gets heated and the junction 2 gets cold. From this we are able to say this Peltier effect is reversible in nature. Next, we are going to see about Peltier coefficient. What is Peltier coefficient? It is the amount of heat energy absorbed or evolved at one of the junctions of a thermocouple when 1 ampere current flows for 1 second. We call that as a Peltier coefficient. It is denoted by pi. Its unit is volt. If H is the quantity of heat absorbed or evolved at one junction, then H is equal to pi I into T. The last effect which we are going to see is Thomson effect, which was given by the scientist named Thomson. According to the Thomson effect, when a current flows through an unequally heated conductor, heat is absorbed or evolved throughout the body of the metal. In Peltier effect, we will be passing the current and heat is absorbed or evolved only at junctions. But in Thomson effect, heat is evolved or absorbed throughout the body of the metal. This is the main difference between Peltier effect and Thomson effect. We are able to classify the Thomson effect into two types. One is positive Thomson effect and another one is negative Thomson effect. In positive Thomson effect, if we are passing the current through a metal which is unequally heated, the first half of the body is heat is absorbed, in the second half of the body heat is evolved. If it is like this means we call this effect to be as the positive Thomson effect. In negative Thomson effect, if we are passing the current through an unequally heated metal, in first half of the metal heat is evolved and in second half of the metal heat is absorbed. So this is the thing which we are having as a difference between positive and negative Thomson coefficient. Let us have some examples for positive Thomson coefficient. These metals such as antimony, silver, zinc and cadmium shows the positive Thomson effect. Similarly, the metals named platinum, bismuth, cobalt, nickel and mercury shows negative Thomson effect. As we saw in Peltier coefficient, here also we are having some other element, peculiar element, which is nothing but lead, which shows the nil Thomson effect. Because in the case of the lead, if we are passing the current through an unequally heated metal body of lead, neither heat is absorbed nor evolved. So hence the Thomson effect is nil in the case of lead. Because of this reason, lead is used as one of the metal to form thermocouple with other metals for the purpose of drawing the thermoelectric diagrams. As we saw in the Peltier effect, in Thomson effect also, we are having Thomson coefficient. The amount of heat energy absorbed or evolved when 1 ampere of current flows for 1 second in a metal between two points which differ in temperature by 1 degree Celsius is called Thomson coefficient. It is denoted by the letter sigma. Its unit is Joule per degree Celsius.